Welcome back everyone. In the last class, we had seen the effects of poles and zeros and also the approximation of higher order systems with second order systems. And I also told you that there is one more specification that we need to go through, which is the steady state error. So today we will dive into steady state error and try to understand what it is. Remember, I had already defined what steady state error is. It is the error between the actual output and the reference signal that you have at t tending to infinity. So let's dive into steady state error. So if you have a standard unity negative feedback configuration of this form, then the steady state error is defined as limit t tends to infinity e of t, where e of t is nothing but the signal RT here or the reference signal minus the signal YT here, which is the actual output. Here is your ET. So at t tending to infinity, whatever is your error, that is what is known as the steady state error of the system. And we can also find out steady state error using the final value theorem, which states that limit of t tending to infinity e of t is nothing but limit of s tending to 0 s of es. Again, you recall when can we apply the final value theorems? You go back to our Laplace transform lecture and then look at that when can we apply final value theorem. All those conditions needs to be satisfied for this formula to be applied. Let's go ahead from this point. So let us try to find out what is ES. ES is nothing but RS minus YS. If I take out RS as common, then we have 1 minus YS by RS, but YS by RS is the closed loop transfer function of this system, which is given by G by 1 plus G. And then if you take LCM here, you will finally get that ES here, the error signal in Laplace domain is nothing but RS by 1 plus GS, where RS is the Laplace transform of the reference input. So now that we have this formula, let us see what will be the steady state error if RS is equal to 1 by S. So if RS is equal to 1 by S, you see this is limit of S tending to 0 S of ES formula we have already found out as RS by 1 plus GS. RS in this case is 1 by S. So we have substituted in place of RS 1 by S, and if you go ahead and complete this calculation, you are left with 1 by 1 plus G0. So ESS, when you give step input, unit step input to the system, is 1 by 1 plus G0. So basically in place of S you put S equal to 0, whatever the transfer function evaluates to at S equal to 0, you can use that to find out the steady state error. So this quantity G0 or limit of S tending to 0 GS is known as position error constant, and we call it Kp. Okay. Now of course you will see that I will use Kp for some other things also. So depending on the context, in today's lecture itself I will use Kp for some other things also. So depending on the context, the meaning of Kp will change. I am just keeping it similar so that it remains same as given in books. So Kp here, we are in this context, in the context of finding out steady state error, Kp here is limit of S tending to 0 GS, which is position error constant, and therefore steady state error is 1 by 1 plus Kp. Now notice that ESS will be 0, that means the steady state error will be 0 when Kp is infinity, which in other words means that if YS has to completely follow the reference signal 1 by S or unit step input, then Kp needs to be infinity. So when you evaluate GS at S equal to 0, the value should come out to be infinity. Next, if we consider ramp input, you go ahead with the same calculations. So ESS in that case will come out to be 1 by limit of S into GS. So this quantity here, limit of S tends to 0, S into GS, is called the velocity error constant Kv. And now the steady state error due to ramp input, unit ramp input is 1 by Kv. So, here these are the specifications that we were talking about. In the previous case, we took unit step signal as the input. In that case, Kp was the specification, that is position error constant. In case of unit ramp input, Kv is the specification, that is velocity error constant, and the error is given by, steady state error is given by 1 by Kv. So, again ESS is 0 when Kv is infinity. Similarly, you can go for an unit parabolic input, that means Rs is equal to 1 by S cube in that case, and if you go ahead with the same type of calculations, you will get what is known as acceleration error constant, and the steady state error will come out to be 1 by Ka. Again steady state error is 0 if Ka is infinity. So, we have got 3 cases for step input, unit step input, for unit step input the specification is Kp and the steady state error is 1 by 1 plus Kp. Okay. For unit ramp input, so for unit ramp input the specification is Kv and the steady state error is 1 by Kv, and for unit parabolic input the specification is acceleration error constant and the steady state error is 1 by Ka. Okay. So, now we will link it up with the type of systems that can be available here. So, let us see another definition which is known as type of a system. So, we already know what order of a system is. What is order of a system? If you take a system, find out its transfer function, the denominator's highest degree is called the order of the system. Now, we are talking of a new definition which is called type of a system. What do you mean by type of a system? So, generally the transfer function of a system Gs can be written in this form. Okay. So, there can be poles, there can be zeros, then s to the power of k, k here can be positive or negative. If it is negative, then this s term will go in the numerator. If it is positive, it is in the denominator. For now, we are considering it to be positive. So, there is in the denominator it is present, say. Now, if here in this case this system will be called a type K system because there are k number of integrators sitting over here. What do you mean by integrator? Integrator, if you remember what is the Laplace transform of integration, it is 1 by s, right. If you do Laplace transform, if Laplace transform of f of t is equal to f of s, then the Laplace transform of integration of f of t dt was equal to this, right. So, due to integration this 1 by s term is coming. So, 1 by s is represents integration. So, how many number of integrators the system has is known as the type of the system, or how many number of poles are there at the origin is known as the type of the system. So, for example, if there are no poles at the origin, consider this transfer function. In this transfer function, if these are all z1, z2, zm, p1, p2, pm, all these are positive integers, not 0, in that case you see there is no pole at the origin for this transfer function. Remember, I am talking about the transfer function Gs. Now, in that case we will call this to be a type 0 system because there are no poles at the origin. So, in that case let us see what will be our error constant. Now, you see what was the error constant? Definition of error constant Kp, or the position error constant. The definition of position error constant was limit of s tending to 0 Gs or G of 0. Now, if you put G of 0 here, this is what you will get. See, the product of Z1, Z2 and Zm, because s equal to 0, and here the product of P1, P2 to Pn. This is what you get, and this is a constant number. This is a constant number. In that case, what will be ESS? ESS will be 1 by 1 plus a constant number here. It is not infinity or 0, it is a constant number. So, which means that we will get a finite steady state error. What is the meaning of getting a finite steady state error practically? Suppose you gave a reference signal. You wanted your output, you want your output to be exactly same as the reference signal, right? Now, if there is a steady state error, finite steady state error, the actual output will not be equal to the reference signal. There will be a difference between the two. We'll take a practical example and see what does that mean also. Okay. So, practically what it means, it is very important. When you have finite steady state error, that means the output is not following the reference trajectory. There is a difference between the two at t tending to infinity, at steady state. Okay. So, for a type 0 system, if a system is type 0, you can guarantee directly looking at the, see, I am just looking at GS, I am not even finding out a transfer function of the entire system, I am just looking at GS. Just by looking at GS, remember again, I am reiterating again, this is a unity negative feedback configuration only that I am talking about, okay. And in this unity negative feedback configuration, what I am trying to do is, I am trying to infer about the outputs difference with the reference for this closed loop system using only the information of GS. I am not even using other information, only the information of GS. I am trying to see what is the steady state error between YS and RS. So, just by looking into GS, since there are no poles at the origin, this is a type 0 system, and directly you can find out Kp. Kp came out to be a finite number, which means there will be a steady state error. So, that means if you give a reference signal, unit step reference signal, or as a matter of fact you can give some any other step reference signal also, because when I am talking about unit step, I can always multiply with some number to make it non-unit step. It can be 2 times of ut, it can be 3 times of ut, you can use the same idea, but whenever there will be a step reference signal, the output is not going to follow the input. There will be a fixed amount of error always for a type 0 system. Okay. So, let us see what about Kv. What if I give a, instead of a step input here, what if I give a ramp input? If I give a ramp input, then Kv is equal to limit of s tending to s of gs, right. So, this becomes s times of this, s of gs means. So, then if you take limit of s gs, it will come out to be 0. Now, if that is 0, then ESS, which was the steady state error, is infinity, which means a type 0 system can never follow a ramp input. For a type 0 system, when you give a step input as reference, it can follow it, but there will be an error between the two. It will not be exactly equal to the reference signal. There will be an error between the two. In case of ramp signal, if you give a ramp reference input, then the error is infinity, means as t tends to infinity, as time increases, the output will be diverging from the reference signal. They will never converge. So, error will keep on increasing. Okay. So, similarly, you do the same thing for parabolic inputs. Again, the same thing will happen. K will be 0, which means steady state error is infinity. So, this tells us that if you have a type 0 system, then it cannot follow a ramp and an parabolic input at all, because the steady state error will keep on growing. The output will diverge from the reference signal, whereas for a step input, it will not diverge, but there will be a fixed error that will be between the reference signal and the output. Okay. So, let us look at a type 1 system. In the similar way, if I go ahead and proceed, so for a type 1 system, we have a pole at the origin. So, if we have a pole at the origin, Kp will come out to be infinity, ESS is 0. That means a type 1 system can follow a step input. So, if you give a step input to the system, type 1 system, then the output will be at t tending to infinity, the output will become exactly equal to the reference signal. Again, remember, I am just talking about unity feedback configuration. There is nothing here. Okay. In one of the classes, I said that if there is non-unity feedback configuration also, you can take it to this form. That I will talk about that soon. Okay. That's a simple algebraic manipulation. Nothing big about it. I'll talk about it. But for now, you see, Kp is infinity, ESS is 0. Okay. Whereas, when I find out Kv, you see what will happen, S into Gs, S and S will cancel out, we will be left with only this part, which means again this will be product of the zeros divided by the product of the poles, and the steady state error will come out to be a finite quantity. Now, you see, in case of a type 1 system, it can follow a step input, but for a ramp input, it will follow it, but there will be a fixed error between the two. It will not exactly reach the reference signal. Whereas for parabolic input, again K comes out to be 0, so steady state error is infinity, but for a parabolic input here, then it is never going to follow it. Type 2 system, by now you must have already understood what is happening. So, for type 0 system, it could not reach the reference value of a step input, but it kept a fixed error. There was a fixed error. For ramp input, it could not follow. For parabolic input, it could not follow. for type 0 systems. Type 1 systems, it could follow step input signals, but it could follow ramp input with a fixed error, but parabolic it could not. So for type 2, what will happen? It can follow step, it can follow ramp, but it will follow parabolic inputs with a fixed amount of steady state error. So let us take an example. Okay, so here is a setup for your speed control of a DC motor. Okay, do you remember what we did for speed control? This was your motor. You found out the transfer function between omega s and the armature voltage, and the transfer function was of this form. If I ask you what is the type of this system, look at this system. If KB, KT, B, J, RA, LA, KT, these are all non-zero quantities, then see they are in the denominator, there are no poles at the origin. So if there are no poles of the origin, we know that this is a type 0 system. Now if it is a type 0 system, what are the things we know? We know that Kp will be finite, Kv will be 0, and Ka will be 0. Okay, so which means that it will follow a step input with a fixed error. Now if I want to control the speed of this motor, okay, so then I will have to design a closed loop configuration of this form, so unity negative closed loop configuration, and the reference signal will be the output that you want. Say suppose example, suppose you want 70 rpm. So what is 70 rpm? What type of a signal is this? So 70 rpm, if this is omega, is this, it's a step input 70. You want that your output should be 70. So this is a step input 70 into ut. Okay, and here I have added a controller. So suppose the controller was not there, Kp is equal to 1, say, then the controller is not there, right? So this is the setup. So what we will do is we will try to see experimentally what happens. So 70 rpm I want to reach, and this is the setup. I will keep Kp equal to 1 first, and then I will change Kp, okay, and see what the effect would be. But theoretically we already know, suppose Kp is equal to 1, this is a type 0 system. I know that omega will not reach 70 rpm, because theoretically we know that there will be a finite steady state error, right? We have already theoretically seen that. If I change Kp to some other value also, then also will it work? Because suppose Kp is some constant, then the Gs is this, then, right? This is the complete Gs then. So then in that case your Gs becomes Kp, Kt into this. Then also the type of the system is not changing, still it is a type 0 system, even when just a constant Kp is being used here. This Kp again, yeah, I told you, right, I am using same symbol for two things now. This Kp is not the position error constant. This is not the position error constant. This is some different Kp. Okay, I mean, I know that you might get confused. This is some constant, say p. This is not position error constant. Okay. So here is the problem statement. So my problem statement is, I want to control the speed of this motor. I want that the output of the motor should be 70 rpm. This is how we proceed. I want the output of this motor to be 70 rpm. So the first thing that you do is you find out the transfer function of the motor, okay, by the methods that we have discussed. So the transfer function of the motor is this, say, okay, with the value with suitable values of the constants. We see that this is a type 0 system, and we know that if it is a type 0 system, there is no way that omega will be able to follow this 70 rpm, because this 70 rpm is a step input, 70 into unit step input, right? So I am adding a controller also. This is a controller. In this sense, we have talked about this, right? I am just adding a constant block here. Changing that constant block changes the closed loop pole locations of this system. I can keep on changing this Kp value, different values, and see how the output will look like. Even then, these two together are also a type 0 system. So still I know that omega will not be able to follow 70 rpm. How are we going to implement this? The idea is similar to what we did for finding out transfer function of this system. Okay, so what we will do is we will use Va to control the output of this system, right? Remember this diagram? This we had discussed while finding out the transfer function of the system. experimentally. So here we have the motor. How do you know what is the RPM of the motor? We will use the encoder. This encoder is interfaced with D3 and D2, say some pin in Arduino Uno, okay, and then using that you will get the value of yt. The reference is already fed inside Arduino Uno. There we are writing a code where we are finding out the error et equal to rt minus yt. The error we have found out, because that we can do, right, inside the Arduino. We wrote down a code and then we multiplied it with kp rt minus yt. This kp is the value that I was talking about, this kp. So this is your et, right. So you see this is your rt, this is your yt. So here we are getting kp rt minus yt. So this is what we will do, okay, and that is what is being done. Now based on whatever output, whatever value that comes out, we will convert that into a PWM signal, okay, and that PWM signal goes through the driver through enable pin, and then finally that leads to the change in input voltage for the DC motor. If your PWM is 255, you get the full voltage, if 255 or 1024 in this case. So depending on what is the resolution of your ADC, so you can change the duty cycle of the PWM based on what is the value of kp into rt minus yt. This is the code, this is the basic code. So the controller has been embedded inside this Arduino itself. Let's see what happens, okay. I am not going into the code, we will discuss the code sometimes later separately, but this is the basic idea. So let's see what happens. So you see the kp value in this video, kp value is 1 here, you can see that, right, and the reference here is 70 as I told, okay. These are the maximum and minimum, so forget about that since I am not discussing the code here. So and forget about the rest of it. So let's see what happens. You can see in the video the motor is here, okay. So let's see. So the motor is running now. You see 70 is the reference, kp is 1. We will look, so we are now uploading the code into the Arduino and we look into the serial plotter. So this is the serial plotter and this is the reference signal 70 and this is the actual signal that you are seeing, okay. So now just look at the actual signal. See, let me just pause it here. Look at the reference signal, this is 70, this is the actual output. You see there is a error. Of course there are fluctuations because this is an experiment, there will be noise in the sensors, etc. Okay, you will not get like simulations, you will get perfect outputs, but here you will not get it. This is experiments, you will have noise and many other external factors that influences the experiments. But at least you can see that there is a steady state error, right, which was expected. What happens if I increase the value of kp? If I increase the value of kp, you see if I increase the value of kp, the steady state error decreases. But does it become 0? No. If you keep on increasing, even then it will not become 0. See, if I make it 5, even then you see the value is not going to 0. It is not reaching the reference at all. Okay. So what to do then? How do I solve this problem? You see, we can easily solve this problem because you see, we know that if it is type 0 system, then we have a problem, right? But what if it is a type 1 system? Can I use something which will convert it to a type 1 system? Because the controller is in my hand, I can design the controller, right? If I change it to a type 1 system, I know that a type 1 system follows a reference input, right? So let us convert it to a type 1 system using this type of a controller. Now what is this controller? You see this is kp, this is ki by s. This kp is the one that we had used and then we have ki by s. So total, what is this? This entire thing is kp plus ki by s. So if it is kp plus ki by s, then what will be the total transfer function? You see, let us see, kp plus ki by s. So this is total equal to kp s plus Ki by S. Okay, so this is the transfer function of this part. This is the total transfer function of this part, Kp S plus Ki by S. And then we have this Gs. So this is your Gs. So total transfer function becomes this part, this entire thing becomes Kp S plus Ki whole into Gs by S, right? And Gs you know is Kt by SLA plus RA whole into Sj plus B plus Kb Kt, right. So, you see now this entire transfer function is a type 1 system. I have converted the system into a type 1 system, and as soon as I convert the system into a type 1 system, I know that it should be following the step input that we had given. So, the values that we just have to choose is Kp and Ki, right. We will choose some arbitrary value for now and let us see what happens. You see now I am giving the value of Ki. Ki is 2, some arbitrary value we have given, and notice what happens. You see the output now is going towards the reference, and see gradually it will go to the reference signal. You see gradually it goes to the reference signal. So, the steady state error is 0, that is what I had already claimed, right, and that is what is happening. So, this is how we design controllers actually. So, in this case you see, in order to remove the steady state error that we were facing, because it was a type 0 system, I added an extra pole at the origin by introducing Ki by S. Okay. And so, since I introduced that, the new system that I get is a type 1 system, and as a result the ramp input was following. So, in this case you see I am able to control the speed. If you change it from 70 to something else, then also it will follow now, but with just Kp value it was not following. Okay. Till now we were looking into the unity negative feedback configuration, and we had defined that steady state error is this. Now, what if we have a non-unity negative feedback configuration? In this case, you can see that the error signal is no longer, the error coming here at this point is no longer RT minus YT. So, hence we can define two types of error in this case. One will be called the output tracking error, which is actually the error between the reference signal and the output signal, and there is something called an actuating error, which is the error at this point, which will be given by this quantity RT minus the signal at this point. Now, what is the signal at this point? The signal at this point is the input at this point, which is YT, convolved with the impulse response of this system, which is H of t, and then RT minus that quantity will give you the actuating error. Now, as soon as we have these two types of error, then the question arises, now whatever we have discussed about type of systems and all, does it make sense here? Can we look at the type of a system and directly conclude that the output tracking error will be 0 or the actuating error will be 0? And the other question is, how do we even define type of a system? Because type of system in the previous case was defined as the number of integrators in the transfer function Gs, the plant transfer function. But now that we have Hs also, which is not equal to 1, so we may have to go for a different definition of type of a system. So let us go ahead and write down the Laplace transform of these equations that we have written. So the output tracking error will be Rs minus Ys, whereas the actuating error will be Rs minus Hs Ys, because the Laplace transform of convolution is multiplication. Now, if I go ahead and find out the quantity E naught S here, which is the Laplace transform of the output tracking error, you can see that Ys by Rs, what is Ys by Rs from this block diagram? We know that Ys by Rs is nothing but G by 1 plus GH, and that is what we will replace here, and the final quantity that we get will be of this form. So this will be our final expression. Whereas for the actuating error, if we do the same thing, and we go ahead and replace ys by rs here by g by 1 plus gh, then you do the simplification, you end up in a expression of this form. Remember, in the unity negative feedback configuration, our error signal here and the error signal, the output tracking error, were the same because hs was equal to 1. And now you can see here that the actuating errors formula is coming out similar to what we got for the unity negative feedback configurations error formula, whereas for the output tracking this is not the same. However, the denominator here is 1 plus gh, and in case of the unity negative feedback configuration, we had the denominator as 1 plus g, and we used this g to define the type of the system. So therefore, in this case, we will define the type of the system as the number of integrators of g into h, instead of number of integrators of g, which was for the unity feedback system. For the non-unity feedback system, the type of a system would be defined by the number of integrators of g into h. Now, if we have the type of the system defined as this, that you can see that in this case, the type of the system would be 1. This is a type 1 system because g into h in this case will come out to be s plus 3 by s into s plus 1. Okay. Now, how does it relate to error constants? We had already found out error constants for unity feedback systems. Now, in this case, again, the error constants will be defined in this way. Kp will be defined as limit of s tends to 0 g into h. In the unity feedback case, it was limit of s tends to 0 g only. Kv, velocity error constant, would be this, and the parabolic error constant would be this. Now, what about the error the steady state actuating error? Now I have to differentiate between what is the meaning of steady state error, so and steady state actuating error. So steady state actuating error is the error at this point at t tending to infinity. So that is the steady state actuating error. Okay, so steady state actuating error will actually be given by 1 by kp, 1 by kv, and 1 by ka. This is similar to what we did for the unity feedback configuration. However, when it comes to the output tracking error, if you find out the steady state for the output tracking error, so the steady state output tracking error is generally what is known as steady state error. Okay, so generally we call this to be the steady state error. What is steady state output tracking error? So steady state output tracking error is the steady state error. Basically, it is the error between the reference and the output as t tends to infinity. Now, in this case, there is no direct relation between the error constants and the steady state output tracking error or steady state error. So we cannot use the error constants in that case. However, we can infer about the steady state actuating error by using the error constants that we have found out. So you can see that for type 0 system, we know that Kp will be finite, Kv 0, Ka 0. Now, steady state actuating error in this case, for for step input it will be finite, for ramp it would be infinite, for parabolic it would be infinite. However, the steady state output tracking error or the steady state error cannot be commented on based on the information about Kp, Kv, and Ka. Similarly, for type 1 system, we already know Kp is infinity, Kv is finite, and Ka is 0. So in similarly, steady state actuating error. So basically, the steady state actuating error is the error at this point. Okay, the error at this point at t tending to infinity goes to 0 for step input. It is finite for ramp input and infinite for parabolic. Again, for output tracking, steady state error we cannot comment on it. Similarly, for type 2 system. So if I have to show you a simulation as to what I mean by that, so let me just try to simulate this point, this example on Simulink. So you can see here, this is the same block diagram that just now I have shown. So what I have done is I have taken the actuating error from this point, put it into the scope, and then I have subtracted the reference signal here from the output signal with this summer, and then put it in the scope. We are calling it the output tracking error, and this is the actuating error. Now if I run this, you can see the actuating error goes to 0 because this was a type 1 system. So for step input the actuating error goes to 0, but you can see that the output is not going to 0. Okay, so the output error is not going to 0. So the output tracking error is 1. So you have to be very careful. I mean, if you have a non-unity negative feedback configuration, then you have to be very careful. You cannot just increase the type of the system and expect that the output will follow the reference signal. However, if you have a unity feedback configuration, then you can directly increase the type of the system and go ahead and say that okay, the system will follow a step input, ramp input, or parabolic depending on the type of the original system. Now comes something that I have kept as a loose end, that I was always telling you that okay, given a non-unity negative feedback configuration, it is always possible to make it into a unity feedback configuration, and this is how we can do that. So if you have a non-unity feedback configuration of this type, so you can actually go ahead and put this through extra summers. Now what are these extra summers doing? Okay, let us look at the signal. So what is the signal coming at this point? The signal coming at this point is yt, and the signal coming at this point is also yt. So the output from this first summer would be RT minus YT, whereas the output from this summer would be RT minus YT plus YT, which means YT and YT will cancel out and you are left with RT. So from this block's perspective, from this inner block's perspective, it is exactly the same system that we are dealing with. All that I have done is I have just added two extra signals and summers, but both this system and these systems are equivalent systems. Basically they behave the same way, so I have not made any change in the transfer function as such. Now notice that this innermost loop here, I know how to convert this into a single block, and I can convert this into a single block using this formula. So G by 1 plus GH, it gets converted into a single block. Similarly, this is another block now, another feedback loop now, positive feedback. So this will get converted to a single block, and now this would be G by 1 plus GH divided by 1 minus, because it is a positive feedback, G by 1 plus GH, and this will come out to be equal to G by 1 plus GH minus S. So this is how you can actually go ahead and convert any non-unity negative feedback configuration to a unity feedback configuration. So I hope you have understood what steady state error is and how we can get rid of that. We can increase the type of a system. Of course, this comes with problems also. If you increase the type of the system, instability also increases. All this we will discuss when we talk about instability as well. But in general, I hope you have understood what is the meaning of steady state error and how can we decrease steady state error in a system. In the next class, we will learn about a very important tool called root locus, and we will see how actually can we come up with these values of Kp, Ki and other types of constants that will be required, and how can we meet the specifications that we want for our system. Thank you.